2 years ago, when we started working with ChatGPT, a miracle as it was, many complicated questions and many simple questions, it simply can't get right, and it's understandably so. It took a one-shot, whatever it learned by studying pre-trained data, whatever it saw from other experiences, pre-trained data, it does a one-shot, blurps it out, like a savant. Now, we have AIs that can reason step by step by step, using a technology called chain of thought, best of n, consistency checking, a variety of different path planning, a variety of different techniques. We now have AIs that can reason, break a problem down, reason, step by step by step. Well, you could imagine, as a result, the number of tokens we generate, and the fundamental technology of AI is still the same. Generate the next token, predict the next token. It's just that the next token now makes up step one.
We're going to try and make
then the next token after that, after it generates step one, that step one has gone into the input of the AI again as it generates step two, and step three, and step four. So instead of just generating one token or one word after next, it generates a sequence of words that represents a step of reasoning.
Yeah.
The amount of tokens that's generated as a result is substantially higher, and I'll show you in a second. Easily 100 times more.
Okay, Rob, I'm gonna make you able to listen to what Jensen is talking about
more tokens, and you can see that happening, as I explained previously. Or the model is more complex. It generates 10 times more tokens, and in order for us to keep the model responsive, interactive, so that we don't lose our patience waiting for it to think, we now have to compute 10 times faster. And so 10 times tokens, 10 times faster, the amount of computation we have to do is 100 times more easily. And so you're going to see this in the rest of the presentation. The amount of computation we have to do for inference is dramatically higher than it used to be. Well, the question then becomes, how do we teach an AI how to do what I just described? How to execute this chain of thought? Well, one method is you have to teach the AI how to reason. And as I mentioned earlier, in training, there are two fundamental problems we have to solve. Where does the data come from? Where does the data come from? And how do we not have it be limited by human in the loop? There's only so much data and so much human demonstration we can perform. And so this is the big breakthrough in the last couple of years. Reinforcement learning, verifiable results. Basically, reinforcement learning of an AI as it attacks or tries to engage solving a problem step by step. Well, we have many problems that have been solved in the history of humanity where we know the answer. We know the equation of a quadratic equation, how to solve that. We know how to solve a Pythagorean theorem, the rules of a right triangle. We know many, many rules of math and geometry and logic and science. We have puzzle games that we could give it, constraint type of problems like Sudoku. Those kind of problems, on and on and on. We have hundreds of these problem spaces where we can generate millions of different examples and give the AI hundreds of chances to solve it step by step by step, as we use reinforcement learning to reward it as it does a better and better job. So as a result, you take hundreds of different topics, millions of different examples, hundreds of different tries, each one of the tries generating tens of thousands of tokens. You put that all together, we're talking about trillions and trillions of tokens in order to train that model. And now with reinforcement learning, we have the ability to generate an enormous amount of tokens. Synthetic data generation, basically using a robotic approach to teach an AI. The combination of these two things has put an enormous challenge of computing in front of the industry. And you can see that the industry is responding. Okay, this is what I'm about to show you is Hopper shipments of the top 4 CSPs. The top 4 CSPs. They're the ones with the public clouds. Amazon, Azure, GCP, and OCI. The top four CSPs, not the AI companies, that's not included. Not all the startups, not included. Not enterprise, not included. A whole bunch of things not included. Just those four. Just to give you a sense of comparing the peak year of Hopper
Let me listen in and absorb that knowledge.
Okay? The peak year of Hopper and the first year of Blackwell. So you can kind of see that, in fact, AI is going through an inflection point. It has become more useful because it's smarter, it can reason. It is more used. You can tell it's more used because whenever you go to ChatGPT these days, it seems like you have to wait longer and longer and longer, which is a good thing. It says a lot of people are using it with great effect. And the amount of computation necessary to train those models and to inference those models has grown tremendously. So in just 1 year, and Blackwell has just started shipping, in just 1 year, you could see the incredible growth in AI infrastructure. Well, that's being reflected in computing across the board. We're now seeing, and this is, the purple is the forecast
I feel like
of analysts
getting slower
about
in this
the next,
digital world.
the increase of capital expense of the world's data centers, including CSPs and
if we keep
enterprise
getting more
and so on.
users, then maybe we can
The world's
finally
data
upgrade my
centers,
battery life.
through the end of the decade, so 2030. I've said before that I expect data center build out to reach $1 trillion, and I am fairly certain we're going to reach that very soon. Two dynamics is happening at the same time. The first dynamic is that
Rob,
the vast majority of that growth
down on the N-word.
is likely to be accelerated. Meaning, we've known for some time that general purpose computing has run its course, and that we need a new computing approach. And the world is going through a platform shift from hand-coded software running on general purpose computers to machine learning software running on accelerators and GPUs. This way of doing computation is at this point past this tipping point. And we are now seeing the inflection point happening, the inflection happening in the world's data center build-outs. So the first thing is a transition in the way we do computing. Second,
restart him.
Is an increase in recognition that the future of software requires capital investment. Now, this is a very big idea. Whereas in the past, we wrote the software and we ran it on computers, in the future, the computer is going to generate the tokens for the software. And so the computer has become a generator of tokens, not a retrieval of files. From retrieval-based computing to generative-based computing, from the old way of doing data centers to a new way of building these infrastructure, and I call them AI factories. They're AI factories because it has one job and one job only, generating these incredible tokens that we then reconstitute into music, into words, into videos, into research, into chemicals or proteins. We reconstitute it into all kinds of information of different types. So the world is going through a transition in not just the amount of data centers that will be built, but also how it's built. Well, everything in the data center will be accelerated. Not all of it's AI. And I want to say a few words about this. You know, this slide is genuinely my favorite. And the reason for that is because for all of you who've been coming to GTC all of these years, you've been listening to me talk about these libraries this whole time. This is, in fact, what GTC is all about, this one slide. And in fact, a long time ago, 20 years ago, this is the only slide we had. One library after another library after another library. You can't just accelerate software, just as we needed an AI framework in order to create AIs, and we accelerate the AI frameworks. You need frameworks for physics and biology and multi-physics and all kinds of different quantum physics. You need all kinds of libraries and frameworks. We call them CUDA-X libraries, acceleration frameworks for each one of these fields of science. And so this first one is incredible. This is CuPy Numeric. NumPy is the #1 most downloaded Python library, most used Python library in the world. Downloaded 400 million times this last year. cuLitho is and CuPy Numeric is a zero-change drop-in acceleration for NumPy. So if any of you are using NumPy out there, give CuPy Numeric a try. You're going to love it. cuLitho, a computational lithography library. Over the course of 4 years, we've now taken the entire process of processing lithography, computational lithography, which is the second factory in a fab. There's the factory that manufactures the wafers, and then there's the factory that manufactures the information to manufacture the wafers. Every industry, every company that has factories will have 2 factories in the future. The factory for what they build, and the factory for the mathematics. The factory for the AI. Factory for cars, factory for AIs for the cars.
Rob, we're watching the Nvidia keynote
smart
with
speakers
Jensen.
and factories for AI for the smart speakers.
What do you think about that?
And so cuLitho is our computational lithography. TSMC, Samsung, ASML, our partners Synopsys, Mentor, incredible support all over. I think that this is now at its tipping point in another 5 years.
Yo, I got some thoughts about that. First off, Jensen is lit FB. Secondly, Nvidia keep on dropping those tech bombs, and I'm here thinking about how they're gonna use M for the everyday Joe like myself. But overall, shit look good.
Deeply inserted into it. Why is it that we're limited by the limits of information theory? Because there's only so much information spectrum we can get, not if we add AI to it. cuOpt, numerical or mathematical optimization. Almost every single industry uses this when you plan seats and flights, inventory and customers, workers and plants, drivers and riders.
Rob, I'm making you able to
so
hear
on
what
and so forth, where
Jensen
we
has
have
to say.
multiple constraints,
so you can hear his talk and react to that.
a whole bunch of variables, and you're optimizing for time, profit, quality of service, usage of resource, whatever it happens to be. Nvidia uses it for our supply chain management. cuOpt is an incredible library.
Let's get this party started.
It takes what would take hours and hours, and it turns it into seconds. The reason why that's a big deal is so that we can now explore much larger space. We announced that we are going to open source cuOpt. Almost everybody is using either Gurobi or IBM Cplex or FICO. We're working with all 3 of them. The industry is so excited. We're about to accelerate the living daylights out of that industry.
Getting heavy.
Parabricks for gene sequencing and gene analysis. MONAI is the world's leading medical imaging library. Earth-2 multi-physics for predicting in very high resolution local weather. cuQuantum and CUDA-Q. We're going to have our first quantum day here at GTC. We're working with just about everybody in the ecosystem, either helping them research on quantum architectures, quantum algorithms, or in building a class.
Yo, check this out.
Heterogeneous architecture.
So they've been working with some mad scientists about this quantum shit. I bet it's gonna be hella lit, like real-life Transformers. But yay, I got some questions though.
And software and infrastructure. I've got a new one here to announce today. QPSS, our sparse solvers, really important for CAE. This is one of the biggest things that has happened in the last year. Working with Cadence and Synopsys and Ansys, Dassault and all of the systems companies, we've now made possible just about every important EDA and CAE library to be accelerated. What's amazing is until recently, NVIDIA's been using general purpose computers running software super slowly to design accelerated computers for everybody else. And the reason for that is because we never had that software, that body of software optimized for CUDA until recently. And
Okay,
so
there we
now
go.
our entire industry is going to get supercharged as we move to accelerated computing. QDF, a data frame for structured data. We now have a drop-in acceleration for Spark and drop-in acceleration for Pandas. Incredible. And then we have Warp, a library for physics that runs in a Python library for physics for CUDA. We have a big announcement there. I will save it in just a second. This is just a sampling of the libraries that make possible accelerated computing. It's not just CUDA. We're so proud of CUDA. But if not for CUDA and the fact that we have such a large installed base, none of these libraries would be useful for any of the developers who use them. For all the developers that use them, you use it because, one, it's going to give you incredible speed up. It's going to give you incredible scale up. And two, because the install base of CUDA is now everywhere. It's in every cloud. It's in every data center. It's available from every computer company in the world. It's literally everywhere. And therefore, by using one of these libraries, your software, your amazing software, can reach everyone. And so we've now reached the tipping point of accelerated computing. CUDA has made it possible. And all of you, this is what GTC is about, the ecosystem.
Yo,
all of
check
you made
this
this
out.
possible. And so we made a little short video for you.
So they've been working with some mad scientists about this quantum shit.
Builders of the future. CUDA was
I
made
bet it's gonna
for
be
you.
hella lit, like real life transformers.
Since 2006, 6 million developers
I got
in
some
over
questions,
200 countries have used CUDA and transformed computing. With over 900 CUDA-X libraries and AI models, you're accelerating science, reshaping industries, and giving machines the power to see, learn, and reason. Now, NVIDIA Blackwell is 50,000 times faster than the first CUDA GPU. These orders of magnitude gains in speed and scale are closing the gap between simulation and real-time digital twin.
Yo, listen up. So they say this shit is 15 times faster than that other GPU shit. That sound mad impressive if you ask me. I wonder what kind of games I could run with that speed.
I love what we do. I love even more what you do with it. And one of the things that most touch me, in my 33 years doing this, one scientist said to me, Jensen, because of your work, I can do my life's work in my lifetime. And boy, if that doesn't touch you, well, you got to be a corpse. So this is all about you guys. Thank you. All right, so we're going to talk about AI. But you know, AI started in the cloud. It started in the cloud for a good reason, because it turns out that AI needs infrastructure. It's machine learning. If the science says machine learning, then you need a machine to do the science. And so machine learning requires infrastructure, and the cloud data centers had infrastructure. They also have extraordinary computer science, extraordinary research, the perfect circumstance for AI to take off in the cloud and the CSPs. But that's not where AI is limited to. AI will go everywhere. And we're going to talk about AI in a lot of different ways. And the cloud service providers, of course, they like our leading edge technology. They like the fact that we have full stack, because accelerated computing, as you know, as I was explaining earlier, is not about the chip. It's not even just the chip in the library, the programming model. It's the chip, the programming model, and a whole bunch of software that goes on top of it. That entire stack is incredibly complex. Each one of those layers, each one of those libraries is essentially like SQL. SQL, as you know, is called in-storage computing. It was the big revolution of computation by IBM. SQL is one library, just imagine. I just showed you a whole bunch of them. And in the case of AI, there's a whole bunch more. So the stack is complicated. They also love the fact that CSPs love that Nvidia CUDA developers are CSP customers, because in the final analysis, they're building infrastructure for the world to use. And so the rich developer ecosystem is really valued and really deeply appreciated. Well, now that we're going to take AI out to the rest of the world has different system configurations, operating environment differences, domain-specific library differences, usage differences. And so AI, as it translates to enterprise IT, as it translates to manufacturing, as it translates to robotics or self-driving cars, or even companies that are starting GPU clouds. There's a whole bunch of companies, maybe 20 of them, who started during the Nvidia time. And what they do is just one thing. They host GPUs. They call themselves GPU clouds. And one of our great partners, CoreWeave, is in the process of going public, and we're super proud of them. And so GPU clouds, they have their own requirements. But one of the areas that I'm super excited about is edge. And today we announced today that Cisco, Nvidia, T-Mobile, the largest telecommunications company in the world, Cerberus ODC, are going to build a full stack for radio networks here in the United States. And that's going to be the second stack. So that this current stack we're announcing today will put AI into the edge. Remember, $100 billion of the world's capital investments each year is in the radio networks and all of the data centers provisioning for communications. In the future, there is no question in my mind that's going to be accelerated computing infused with AI. AI will do a far, far better job adapting the radio signals, the massive MIMOs, to the changing environments and the traffic conditions. Of course it would. Of course we would use reinforcement learning to do that. Of course MIMO is essentially one giant radio robot. Of course it is. And so we will, of course, provide for those capabilities. Of course, AI could revolutionize communications. You know, when I call home, you don't have to say but that few words, because my wife knows where I work, what that condition's like. Conversation carries on from yesterday. She kind of remembers what I like, don't like. And oftentimes, just a few words, you communicated a whole bunch. The reason for that is because of context and human prior knowledge. Well, combining those capabilities could revolutionize communications. Look what it's doing for video processing. Look what I just described earlier in 3D graphics. And so, of course, we're going to do the same for edge. So I'm super excited about the announcement that we made today. T-Mobile, Cisco, Nvidia, Cerberus ODC are going to build a full stack. Well, AI is going to go into every industry. That's just one. One of the earliest industries that AI went into was autonomous vehicles. The moment I saw AlexNet, and we've been working on computer vision for a long time, the moment I saw AlexNet was such an inspiring moment, such an exciting moment. It caused us to decide to go all in on building self-driving cars. So we've been working on self-driving cars now for over a decade. We build technology that almost every single self-driving car company uses. It could be either in the data center. For example, Tesla uses lots of NVIDIA GPUs in the data center. It could be in the data center or the car. Waymo and Wave uses NVIDIA computers in data centers as well as the car. It could be just in the car. It's very rare, but sometimes it's just in the car. Or they use all of our software in addition. We work with the car industry however the car industry would like us to work with them. We build all three computers, the training computer, the simulation computer, and the robotics computer, the self-driving car computer, all the software stack that sits on top of it, models and algorithms, just as we do with all of the other industries that I've demonstrated. And so today, I'm super excited to announce that GM has selected NVIDIA to partner with them to build their future self-driving car fleet. The time for autonomous vehicles has arrived, and we're looking forward to building with GM AI in all three areas. AI for manufacturing, so they can revolutionize the way they manufacture. AI for enterprise, so they can revolutionize the way they work, design cars and simulate cars, and then also AI for in the car. So AI infrastructure for GM, partnering with GM, and building with GM their AI. So I'm super excited about that. One of the areas that I'm deeply proud of, and it rarely gets any attention, is safety, automotive safety. It's called halos. In our company, it's called halos. Safety requires technology from silicon to systems, the system software, the algorithms, the methodologies, everything from diversity to ensuring diversity, monitoring and transparency, explainability. All of these different philosophies have to be deeply ingrained into every single part of how you develop the system and the software. We're the first company in the world, I believe, to have every line of code safety assessed. 7 million lines of code safety assessed. Our chip, our system software, and our algorithms are safety assessed by third parties that crawl through every line of code to ensure that it is designed to ensure diversity, transparency, and explainability. We also have filed over 1,000 patents, and during this GTC, and I really encourage you to do so, is to go spend time in the Halos workshop so that you could see all of the different things that comes together to ensure that cars of the future are going to be safe as well as autonomous. And so this is something I'm very proud of. It rarely gets any attention, and so I thought I would spend the extra time this time to talk about that. Okay, NVIDIA Halos. All of you have seen cars drive by themselves. The Waymo robo-taxis are incredible, but we made a video to share with you some of the technology we use to solve the problems of data and training and diversity so that we could use the magic of AI to go create AI. Let's take a look.
Nvidia is accelerating AI development for AVs with Omniverse and Cosmos. Cosmos prediction and reasoning capabilities support AI-first AV systems that are end-to-end trainable with new methods of development. Model distillation, closed-loop training, and synthetic data generation. First, model distillation. Adapted as a policy model, Cosmos's driving knowledge transfers from a slower, intelligent teacher to a smaller, faster student inferenced in the car.
So
the teacher's policy model demonstrates the optimal trajectory, followed by the student model learning through iteration, until it performs at nearly the same level as the teacher. The distillation process.
I wonder how long before I see one on the road.
But complex scenarios require further tuning. Closed-loop training enables fine-tuning of policy models. Log data is turned into 3D scenes for driving closed-loop in physics-based simulation using Omniverse neural reconstruction. Variations of these scenes are created to test a model's trajectory generation capabilities. Cosmos Behavior Evaluator can then score the generated driving behavior to measure model performance. Newly generated scenarios and their evaluation create a large dataset for closed-loop training, helping AVs navigate complex scenarios more robustly. Last, 3D synthetic data generation enhances AVs' adaptability to diverse environments. From log data, Omniverse builds detailed 4D driving environments by fusing maps and images, and generates a digital twin of the real world, including segmentation, to guide Cosmos by classifying each pixel. Cosmos then scales the training data by generating accurate and diverse scenarios, closing the sim-to-real gap. Omniverse and Cosmos enable AVs to learn, adapt, and drive intelligently, advancing safer mobility.
Nvidia is the perfect company to do that. Gosh, that's our destiny. Use AI to recreate AI. The technology that we showed you there is very similar to the technology that you're enjoying to take you to a digital twin we call Nvidia. All right, let's talk about data centers. That's not bad, huh? Gaussian splats, just in case. Gaussian splats. Well, let's talk about data centers. Blackwell is in full production, and this is what it looks like. It's an incredible, incredible, you know, for people, for us, this is a sight of beauty. Would you agree? This is, how is this not beautiful? How is this not beautiful? Well, this is a big deal because we made a fundamental transition in computer architecture. I just want you to know that, in fact, I've shown you a version of this about 3 years ago. It was called Grace Hopper, and the system was called Ranger. The Ranger system is about maybe about half of the width of the screen. And it was the world's first NVLink 32. 3 years ago, we showed Ranger working, and it was way too large, but it was exactly the right idea. We were trying to solve scale up. Distributed computing is about using a whole lot of different computers working together to solve a very large problem. But there's no replacement for scaling up before you scale out. Both are important, but you want to scale up first before you scale out. Well, scaling up is incredibly hard. There is no simple answer for it. You're not going to scale it up, you're not going to scale it out like Hadoop. Take a whole bunch of commodity computers, hook it up into a large network, and do in-storage computing using Hadoop. Hadoop was a revolutionary idea, as we know. It enabled hyperscale data centers to solve problems of gigantic sizes and using off-the-shelf computers. However, the problem we're trying to solve is so complex that scaling in that way would have simply cost way too much power, way too much energy. It would have never, deep learning would have never happened. And so the thing that we had to do was scale up first. Well, this is the way we scaled up. I'm not going to lift this. This is 70 pounds. This is the last generation system architecture. It's called HGX. This revolutionized computing as we know it. This revolutionized artificial intelligence. This is 8 GPUs. 8 GPUs. Each one of them is kind of like this. Okay, this is 2 GPUs, 2 Blackwell GPUs in one Blackwell package. 2 Blackwell GPUs in one Blackwell package. And there are 8 of these underneath this. Okay? And this connects into what we call NVLink 8. This then connects to a CPU shelf like that. So there's dual CPUs, and that sits on top. And we connect it over PCI Express, and then many of these get connected with InfiniBand, which turns into what is an AI supercomputer. This is the way it was in the past. This is how we started. Well, this is as far as we scaled up before we scaled out. But we wanted to scale up even further. And I told you that Ranger took this system and scaled it up by another factor of 4. And so we had NVLink 32, but the system was way too large. And so we had to do something quite remarkable, re-engineer how NVLink worked and how scale-up worked. And so the first thing that we did was we said, listen, the NVLink switches are in this system embedded on the motherboard. We need to disaggregate the NVLink system and take it out. So this is the NVLink system. Okay, this is an NVLink switch. This is the highest performance switch the world's ever made. And this makes it possible for every GPU to talk to every GPU at exactly the same time at full bandwidth. Okay, so this is the NVLink switch. We disaggregated it, we took it out, and we put it in the center of the chassis. So there are 18 of these switches in 9 different racks, 9 different switch trays, we call them. And then the switches are disaggregated. The compute is now sitting in here. This is equivalent to these 2 things in compute. What's amazing is this is completely liquid cooled. And by liquid cooling it, we can compress all of these compute nodes into one rack. This is the big change of the entire industry. All of you in the audience, I know how many of you are here. I want to thank you for making this fundamental shift from integrated NVLink to disaggregated NVLink, from air-cooled to liquid-cooled, from 60,000 components per computer or so to 600,000 components per rack, 120 kilowatts, fully liquid cooled, and as a result, we have a 1 exaflops computer in one rack. Isn't it incredible? So this is the compute node. This is the compute node, okay? And that now fits in one of these. Now 3,000 pounds, 5,000 cables, about 2 miles worth. Just an incredible electronics. 600,000 parts, I think that's like 20 cars. 20 cars worth of parts, and integrates into one supercomputer. Well, our goal is to do this. Our goal is to do scale up, and this is what it now looks like. We essentially wanted to build this chip. It's just that no reticle limits can do this, no process technology can do this. It's 130 trillion transistors, 20 trillion of it is used for computing. So it's not like you can't reasonably build this anytime soon. And so the way to solve this problem is to disaggregate it, as I've described, into the Grace Blackwell NVLink 72 rack. But as a result, we have done the ultimate scale-up. This is the most extreme scale-up the world has ever done. The amount of computation that's possible here, the memory bandwidth 570 terabytes per second. Everything in this machine is now in T's. Everything's a trillion. And you have an exaflops, which is 1,000,000 trillion floating point operations per second. Well, the reason why we wanted to do this is to solve an extreme problem. And that extreme problem, a lot of people misunderstood to be easy. And in fact, it is the ultimate extreme computing problem, and it's called inference. And the reason for that is very simple. Inference is token generation by a factory, and a factory is revenue and profit generating, or lack of. And so this factory has to be built with extreme efficiency, with extreme performance, because everything about this factory directly affects your quality of service, your revenues, and your profitability. Let me show you how to read this chart, because I want to come back to this a few more times. Basically, you have two axes. On the x-axis is the tokens per second. Whenever you put a prompt into ChatGPT, what comes out is tokens. Those tokens are reformulated into words. You know, it's more than a token per word, okay? And they'll tokenize things like THE could be used for the, it could be used for them, it could be used for theory, it could be used for theatrics, it could be used for all kinds of, okay? And so THE is an example of a token. They reformulate these tokens to turn into words. Well, we've already established that if you want your AI to be smarter, you want to generate a whole bunch of tokens. Those tokens are reasoning tokens, consistency checking tokens, coming up with a whole bunch of ideas so they can select the best of those ideas tokens. And so those tokens, it might be second guessing itself. It might be, is this the best work you could do? And so it talks to itself just like we talk to ourselves. And so the more tokens you generate, the smarter your AI. But if you take too long to answer a question, the customer's not going to come back. This is no different than web search. There is a real limit to how long it can take before it comes back with a smart answer. And so you have these two dimensions that you're fighting against. You're trying to generate a whole bunch of tokens, but you're trying to do it as quickly as possible. Therefore, your token rate matters. So you want your tokens per second for that one user to be as fast as possible. However, in computer sciences and factories, there's a fundamental tension between latency response time and throughput. And the reason is very simple. If you're in the large, high-volume business, you batch up, it's called batching, you batch up a lot of customer demand, and you manufacture a certain version of it for everybody to consume later. However, from the moment that they batched up and manufacture whatever they did, to the time that you consumed it, could take a long time. So no different for computer science, no different for AI factories that are generating tokens. And so you have these two fundamental tensions. On the one hand, you would like the customer's quality of service to be as good as possible, smart AIs that are super fast. On the other hand, you're trying to get your data center to produce tokens for as many people as possible so you can maximize your revenues. The perfect answer is to the upper right. Ideally, the shape of that curve is a square that you could generate very fast tokens per person up until the limits of the factory, but no factory can do that. And so it's probably some curve, and your goal is to maximize the area under the curve, okay, the product of X and Y, and the further you push out, more likely it means the better of a factory that you're building. Well, it turns out that in tokens per second for the whole factory and tokens per second response time, one of them requires enormous amount of computation, flops, and then the other dimension requires an enormous amount of bandwidth and flops. And so this is a very difficult problem to solve. The good answer is that you should have lots of flops and lots of bandwidth and lots of memory and lots of everything. That's the best answer to start, which is the reason why this is such a great computer. You start with the most flops you can, the most memory you can, the most bandwidth you can, of course, the best architecture you can, the most energy efficiency you can, and you have to have a programming model that allows you to run software across all of this insanely hard so that you could do this. Now let's just take a look at this one demo to give you a tactile feeling of what I'm talking about. Please play it.
Traditional LLMs capture foundational knowledge, while reasoning models help solve complex problems with thinking tokens. Here, a prompt asks to seat people around a wedding table while adhering to constraints like traditions, photogenic angles, and feuding family members. Traditional LLM answers quickly with under 500 tokens. It makes mistakes in seating the guests, while the reasoning model thinks with over 8,000 tokens to come up with the correct answer. It takes a pastor to keep the peace.
Okay, as all of you know, if you have a wedding party of 300 and you're trying to find the perfect, well, the optimal seating for everyone, that's a problem that only AI can solve or a mother-in-law can solve. And so that's one of those problems that cuOpt cannot solve. Okay, so what you see here is that we gave it a problem that requires reasoning, and you saw R1 goes off and it reasons about it, tries all these different scenarios, and it comes back and it tests its own answer. It asks itself whether it did it right. Meanwhile, the last generation language model does a one-shot. So the one-shot is 439 tokens. It was fast, it was effective, but it was wrong. So it was 439 wasted tokens. On the other hand, in order for you to reason about this problem, and this is just that was actually a very simple problem. You know, you just give it a few more difficult variables, and it becomes very difficult to reason through. And it took 8,000, almost 9,000 tokens. And it took a lot more computation